Ok ragazzi, cominciamo? Okay, last time we refreshed a little bit the notion of process and thread. Thread not yet. We just reminded what happens whenever there is a context switch, whenever an interrupt arrives, whenever there is a scheduling decision, something needs to be saved, then there is a context switch and a new process starts. There are many different schedulers. One of the oldest one, most typical or naive one, can be a time trigger scheduling. Time trigger. This is typically used especially in the avionic domain. So in this scheduler, you have a scheduling table and you specify from scratch when each task should execute. So you have a table with task activation time, task scheduling time, and you say at instant 1 it's task 2 that executes for 3 milliseconds, then it's task 4 that executes for 4 milliseconds, and so on. Okay, these are called time sharing systems, or time triggered, okay, or time driven, and are in contraposition to event driven. So these two paradigms are alternative, orthogonal. So time driven, you have like a tick that mandates when each job executes. If one of the jobs or tasks executes for less than its slot, typically you waste some idleness, some time, okay, some processing time, because there is no useful use of it. Okay, there are ways to counterbalance it, but typically it relies on a scheduling table, which is computed offline and used online to decide which process executes next. Okay, these are time sharing systems. The alternative is an event sharing system, where you have some kind of an event-driven way to activate tasks. So you don't have a table where you know in advance when each task will execute, but you just wait for events to activate a task. It can be an external interrupt that activates a task, or it can be another task that activates that task. Okay? It can be multiple factors that activate that task. The operating system is noticed that someone would like to execute, and you typically have a scheduling queue, okay, a ready queue, and it is sorted according to one of the policies that we mentioned last time, and you take the next task to execute from this ready queue. Okay? You don't have a scheduling table, you have an event-driven activation of tasks which are put in a ready queue and executed from there. Okay? Time-driven versus event-driven. So time-driven, in time-sharing system, for instance, assume you have a slot of 10 milliseconds. Okay, so 10 milliseconds is the slot for each task to execute. So at the end of the round of the 10 milliseconds, the processor is given to another process. Okay, so you typically have the yellow task, for instance, that starts and executes on the CPU. As soon as the 10 milliseconds are over, you typically have a timer that signals that the slot is over, so that the operating system proceeds to a context switch, deschedules that task, reinserts it at the end of the queue or whatsoever, and executes the next red task. Okay? So this is like a very simple mechanism. It's predictable, it's very predictable because you really know at every time which task executes. Okay? You have a scheduling table. In the avionic domain, really everything should work in a predictable way, so you know when each task executes and when, okay, and for how long. So when an interrupt arrives, independently you are using an event-driven or a time-triggered scheduler, you still have the notion of interrupt. In time-driven, it's given it's a timer interrupt. In the other case, can be whatever. Okay. So what happens when an interrupt arrives? Typically, you change to supervisor mode, to the privileged mode. Okay. It's the operating system that deals with interrupt. It's not your task. Okay. It's the operating system that has an interrupt service routine. So you typically need to change from user mode to privileged mode, okay? Then you save the context of the interrupted task, okay? So control register, instruction pointer, registers that are used and dirtied by the preempted task, and so on. Why do you save them? Because then you would like, when the interrupt service is over, you would like to resume the task that has been interrupted. Then you execute the interrupt handler, okay? You call the scheduler at the end of the interrupt handler. Why is that? In an event-driven paradigm, whenever an interrupt arrives, this interrupt can activate potentially a new task. So you need to take a scheduling decision there, okay? So when the scheduling should change in an event-driven paradigm, when you have something, a potential activation of some high priority task or whatsoever, right? So an interrupt is a typical instance that can activate a new task instance. So you need, at the end of the interrupt service, you need to recall the scheduler, okay, in a preemptive operating system. This typically may change if the activated task has a higher priority. This may lead to a change in the exec pointer, and then you call the erect. Erect is the interrupt return, so it's the typical instruction. It may vary from architecture to architecture, but it is the instruction that pops the registers that have been saved, restores the context, and continues the execution. Okay, and rechange back from supervisor mode to user mode. Okay, so this is like fairly typical. It may vary from architecture to architecture, but this is a fairly typical behavior of an interrupt that causes a process switch. Other causes for a process switch may be voluntary. So a process may call a blocking primitive. What is a blocking primitive? For instance, a wait primitive. A process is executing, and either it would like to synchronize on a shared resources or a semaphore, or it needs to wait a second task to reach a certain step of the code, or it can just sleep for 5 milliseconds for any reason. Okay? This is a blocking primitive. What is blocking? Blocking means that the task that was running goes to blocking state. So it relinquishes the processor to other activities. Okay? So it does not monopolize the processor, the processing bandwidth, either voluntarily or involuntarily. Okay? So if it is voluntary, then it means that it may have called a read, an OS primitive, a wait, or sleep, or whatsoever. Okay? If it is not voluntary, then it may mean that an interrupt has arrived and maybe activated a higher priority task. Okay? Or you reached, in a time sharing system, the timer slot, okay, the end of the time slot. Okay? or it can be an I/O device. Okay, for instance, the task was waiting, a high priority task was waiting for a packet to arrive at the Ethernet port. Okay, you know how it works, right? So there is a controller, the Ethernet controller, that may send an interrupt to the processor and signal that a new packet, a new message arrived, and the OS has to deal with that. Okay? If the task that deals with that has a high priority, then it may lead to a context switch, to a process switch. When we talk about processor, these are things that you should already know from your bachelor studies. When we talk about processors, we divide into resource ownership and scheduling / execution. So resource ownership means that the process comes with a notion of a given domain, a given set of resources, a given memory space that the process owns. So the process is the proprietary of a given address space, address range. So it has a virtual address space and a process image. So you remember the memory that we depicted in one of the previous slides, the stack, the heap, the code, text, and so on. That is proprietary of the process. Okay? So a process is not just the execution, it's also like a context. The memory address space, the code, the data. Okay? It can be also allocated a set of resources, file descriptors, I/O channels, and so on. Okay? A process may be the exclusive proprietary of some of these resources. Okay? And then with this we already said, right, that the execution of a process may change from ready, running, blocked. Okay, it follows a sequence of internal states. Okay, and it may come with a set of scheduling parameters. We may associate a priority to a process if we are using a priority-driven scheduler. We may associate to a process a deadline or the time until its deadline. Okay, so if the file descriptors has some information of this kind, of course, these are property of the process. And if we want to further separate these two aspects, so the flow of execution and the property of the resources, okay, the ownership of the resources, we say that the process is the owner of resources. The thread is the execution flow. Okay, let's get back to that. So process is the resource owner. So the process is not only the execution flow, but also it comes with the process state, with a set of memory addresses, and so on. While the thread is the execution flow only, without this notion of ownership of resources. So the thread is the scheduling entity. So you do not schedule the virtual memory addresses. You schedule the execution flow on the cores, right? So you schedule threads, okay? So one process may consist of one or more threads. You may have in multi-threaded OSs, you may have one process, memory space, and set of assigned resources, which are used by not just one thread, but by multiple threads that concurrently operate on the shared memory address space, on the shared set of resources. Okay? So multiple flows of execution, multiple threads may act on the same set of shared resources of the same process. Okay? Thread, process.
Could you explain the scheduling entity?
Yeah, so scheduling entity means what do we schedule typically in an operating system? We schedule the processor time, right? We schedule the processor time. So we would like to know, we don't schedule the memory addresses. We also do somewhat, but I mean, the typical scheduler, what it does is allocating the processing bandwidth, okay? So now it's turn off thread 1, then I execute the high priority thread 0, then thread 4, okay? So I'm executing and scheduling the processor time, okay? So the processor time means which execution flow will I execute next. So the owner, the entity that determines the execution flow is the thread. Okay, thread is an instance, okay, of an execution flow of a program. Okay, if I can run the same program twice, it's one thread, another thread, and they may share the same process space. Okay, or they may have different programs. They may be different programs. One task has a thread 250, one task has the thread 340, and they share the same address space in a multi-threaded environment. Okay, so that is the single process, multi-thread. I schedule the thread before this one, and then this one, then again this one. Okay, so this is the scheduling entity. We will schedule threads. Okay. Okay, threads are in some cases, it was also in Linux that way, so lightweight processes. Because also in the process you have the notion of execution flow, right? But it comes also with resource ownership. Threads take out the part of resource ownership, so they are kind of lightweight processes. Okay? They are sometimes also called that way. So one process may have many different and concurrent threads, okay? Many different traces of execution, many different execution flows, okay? But one thread may not belong to two processes. One thread belongs only to one process, okay? A process may be mapped to multiple threads, but each thread may be mapped to at most one process, okay? It cannot be the owner of multiple memory regions, okay? And no thread can exist outside a process. Okay? A thread is always associated with a given process. Okay? Is it clear? Did you see already these things in operating system courses? More or less? Okay, not so much. It was good to re-summarize them again. Just to clarify it better with a few examples, graphical examples, this is a single-threaded process model, okay? One process, one thread, so not multi-threaded, okay? So in the single-threaded process model, one process has only one thread, okay? So you have a one and only one address space, one and only one stack, one and only one process control block, okay? So user stack, you may have kernel stack, you may have, depending if you are in user mode or supervisor mode. Okay, these are two different stacks. Then you have a unique process control block and a unique user address space. Okay, this is the simple case of a single thread. When we go to multi-threaded process model, so one process multi-thread, multiple threads, then you still have a unique process control block and a unique user address space, which is operated by not only one thread, but by multiple threads. Okay, they share the same user address space and the same process ID and control block. Okay, so each thread may have user mode or supervisor mode. So the kernel stack, so the associated, when I change mode, when I do a mode switch, also the stack pointer and everything changes, right? So because they should act, the different supervisor and user mode, they should act on different regions, different data, right? So the thread may have different stacks for user mode and kernel mode, right? Plus, it has a lightweight control block, which is the thread control block. So these are the thread-specific information which are owned by the thread itself. Everything else is shared among all the threads. And note again that two different threads have two different stacks. Okay? So the stack, you remember the stack, that part of the memory that changes dynamically, increasing in one direction and decreasing in the other direction, right? So the stack is typically owned by the thread. The rest of the memory space is shared among all threads. Okay? There are ways in C and C++ to specify which part is shared, which part is not, with the operating system primitives and so on. Yeah.
Why change from user mode to kernel mode to supervisor mode? All thread change or only interested?
Only it depends on where do you route for instance, if an interrupt arrives and that interrupt is assigned to core 1 where the thread 1 is executing, then it's that thread, I mean it's not the thread, it's the core that changes to supervisor mode. So it's not like a thread specific change of, in that case. If it is the thread itself that calls an OS primitives, then it is the thread itself that goes to kernel mode and kernel stack. Okay. Okay. So threads generally do not share memory. Processes generally do not share memory. So you typically, when you need to share memory between two concurrent activities, you use different threads and the same process. Okay? It is possible to share also between processes, but it's somewhat more complex and has a higher overhead. Threads are thought exactly for sharing, for concurrently working, cooperatively working on a same set of resources belonging to the same process. To communicate between processes, you need to use OS primitives. So there are operating system primitives that allow you to communicate between two different processes. Okay? And processes are much heavier than threads. Why they are much heavier? Because they come with an associated memory region. So when you have a process switch, you need to save much more things that you need to save in a thread switch. Again, when you change process, when you do a process switch, okay, there are much more things to save. Okay, there is a larger overhead than when you do a thread switch. Threads are much lighter. You saw that there are much less things associated to a thread than to a process. So a thread switch is much more convenient than a process switch. Okay? Thread is much more lightweight. And in process, we need to change, when you have a process switch, you need to change the address space. Okay? Virtual memory, the address space will change when you change from process A to process B. In the thread change, the address space will remain the same. Okay? Much less overhead. So it's much also lighter to communicate between two different threads than it is between two different processes. Again, between processes you have OS primitives, but between threads this is native because they share the same memory. Okay? Besides the stack, they have a dedicated memory, they belong to the same process. You don't have any segmentation fault when you try to access another thread memory region because it's the same memory region of yours. Okay? So the thread switch is much lighter. Okay? And so this slide comes with some more semantic notions, some more philosophical differences between processes and threads. So when do you use a process, when do you use a thread? So you use threads when you would like to achieve something in a cooperative way. If you have multiple flows of execution that cooperate to the same goal. In that sense, you will use multiple threads belonging to the same process. Again, we said it already. So if we need that a set of activities cooperates for achieving something, so they are not completely separated entities. At some point, maybe one thread will need to use the partial result of the first one. Okay? Or maybe the second thread may have a larger period which executes every two times the execution of the first one. Or they wait each other to synchronize before continuing together. I don't know. There are many things. So if you are designing your game, there is the sprint, okay? So one thread is updating one non-plane player, and the other one is updating the background, while the other one is doing something else. So they are sharing the screen, so the memory region that belongs to the screen. So typically threads work on similar set of resources, either to communicate between each other, or to synchronize between each other, or to modify the same set of shared resources. Okay? Processor, two different processors, not. When you use processor when you have like a competing scenario. So one processor acts on the printer, one processor acts on the display, for instance, which need to do something completely different memory region, completely different activities. They are not cooperating. For instance, I'm using my email client while I'm downloading something else to see later. So these are two different processes. They do not share typically any memory region. Okay, so they do not cooperate, but rather they compete. They compete for obtaining the processor. They compete for obtaining the processing bandwidth of your processor. Okay, so this is the two different concepts when you use processors and when you use threads. Okay. Yeah. Of course, in a multiprocessor machine, two threads are not only concurrent, but they may even run in parallel. Okay? So this is something that we teach in a course, in a computer science course, which I'm starting next week, parallel computing. Okay, we teach how to use the parallel processing machine, so taking a further step beyond the concurrency. Okay? Okay, just again to simplify further, you may ask yourself, why do I need concurrency? Why do I need threads? Okay, why not just executing one activity after another? There are still many people in industry that do not use concurrency. A lot of industry, even advanced industry, do not use concurrency. You will notice that. You will notice that when you will go to work. So even big industry that still have motion and control stacks, application that basically say, okay, from here to here this task, and then continue, and then every 2 periods you execute this, and then that. So one single task, okay, specifying all the code, all the function call, okay, and if one task needs to execute 4 times faster than the first one, then you have 4 function call to 1 in a single iteration of the whole loop. So it's a very not efficient way of doing things. It's just the first way that I would do if I ask you, when I ask your colleagues of the first year degree in the computer science course, the other department to run a project, to do a project, I'm also assigning them a similar tasks as I will be assigning to you, just they are in the first year, they don't know concurrency, they don't know threads, they don't know real-time scheduling, they don't know shared resources. So they just use Allegro library or whatsoever, Qt, to do a game, right? But that game is single task, okay? So typically in their code, you have a structure of this kind. This is something you would do if you don't know concurrency, okay? Just one single cycle with function calls that maybe operates with the same resources, but there is no concurrency in it. Why do I need concurrency? Take a simple example of a word processor. For instance, I will need first to wait for the input from the keyboard, okay? Then, when this input arrives, then I need to update the document, okay? So, if I wrote a T, then I would like the document to have a T, okay? Then maybe I need to format the document. Maybe I need to open a new line or, I don't know, something like that. Then I will need maybe to check for syntax errors, okay? If I have the spell checker on. Then I may check for other events, if it is time to save the whole document, okay? And then return to 1, okay? Typically, if you don't know anything about concurrency, you would do that in one single process, okay? One single thread. So that would be the outcome of it. What can be the problem? So the problem is that most of the time, the computer is much faster than our time of reaction. So most of the time, the computer is waiting for input from your side. So step 1 takes a lot of time. So most of the time, the program waits for your input. input. So while we wait, can we perform some other task? That's the notion of concurrency. So don't waste that time that you spend waiting for like the user to push a button and then insert the next letter. So while you wait, maybe you can do activities 3 and 4, which were formatting and syntax checking, okay, while you wait for next events, okay? This you can only do if you don't have just one process, but if you split execution between 2 or 3 different processes activities, okay, concurrent activities. So you can have one process that waits for input, another process that periodically formats the document, a third one that has syntax checking, and a fourth one that visualizes the content of the document, okay? So in that sense, everything is much faster. Note that I'm speeding up execution despite I'm not having a parallel architecture. I'm not having a multi-core here. I still have a single core, but concurrency allows you to speed up things. So while I wait, I perform some more meaningful activity. Okay? If I haven't had the concurrency, then I always need to wait for the user to press a button before doing everything else, okay? Instead, with a concurrent activity, while I wait for something, I can perform something else. What happens at low level in that sense? We just saw it in the previous slides. So that's a blocking primitive. So instead of actively waiting for the user to press a button, they do that in a for loop wait for event. So, for loop maybe check whether it's a polling, it's an active polling, check whether the user pushed the button. Instead you can do a blocking primitive. So you can put the input process in a blocking state, okay? It will be waken up by an interrupt when the user presses the keyboard. Let me re-explain that. So in the previous slides we had, this is the waiting time, right? Single thread environment. Here, instead of actively polling, did you insert, I just do, okay, block, and I will be waken up when an interrupt arrives, signaling that the user pressed the button. Okay? So all this time, I can execute the next activities. As soon as the input task is waken up by the interrupt, then I can acquire the new letter that the user inserted. Okay? So I'm not using multi-cores, I'm using single cores, but I'm making better use of the waiting time for events. Okay? This is concurrency useful for a single core scenario. Of course, then if you have a multi-core, it's trivial that you have a speed up if you have a concurrent expression of your application. Is it clear? So when you have multiple processes, and all processes need to access the same data structure, you need to decide which process holds the data structure. So I'm not using multi-threaded, but I'm using here multi-process. Okay? I have different processes that perform different activities, but they need to share at some point data structure. Okay? Shared resource. So I need to define which process holds the data structure. Okay? There are multiple solutions in this sense. A typical one, when you have multi-process environment, is message passing. So again, here I don't have multiple threads sharing the same address space. Here I have multiple processes, each one with its own address space, but I need them to communicate and share a resource. Okay? So the message passing solution is to dedicate another process as the manager of that shared resource. Okay? A manager of that shared resource. So A dedicated process holds the data, is the one that owns the memory space associated with the shared memory region, and it also comes with primitives, with an API, with an interface for the other process to access its owned memory region. Okay? This is a message passing way to implement communication and sharing in multi-process environment. Okay? This is less efficient than the multi-thread. Okay? Can you guess why? So why is the communication here less efficient than in a multi-thread setting? Try. Nessuno rischia?
Because you must change the address space.
Exactly. Obviously, yes, you need to do a process switch every time you need to communicate. While in a multi-threaded environment, this is natively supported. You don't need to change the address space. Okay? So shared memory is more efficient, depending on the architecture, than message passing. Okay? Message passing is typical of competing environment when you have different processes that at some point need to communicate with each other, while you use shared memory for cooperative environment in a multi-thread setting. You don't need a process switch whenever a thread, a task needs to communicate to a different activity. Ok? Mi seguite, che vedo che non annuite, quando non annuite mi preoccupo. Se sono problemi ditemi, lo posso anche rispiegare. Chiaro? Ok? So the other one is a shared memory. And of course, one process holds the data and makes that part of its memory shareable with the others. Okay? If it is performed in a multi-threaded setting, then it's okay. If it is performed in a multi-process setting, then I'm ending up again on a less efficient solution because I would still need a process switch, which is something that you would like to avoid. Okay? So, summarizing, why using threads? Threads allow you a much higher speed of creation, for instance. So when I want to create a new thread, I have much less data structure to initialize. Okay? It's a much lighter process to create a new thread rather it is to create a new process. When I switch from thread to thread, it's a much faster process than when I switch from process to process. Okay? Thread natively support a shared memory paradigm, okay, because they share the same set of memory region, the set of virtual addresses, okay, and they can naturally access the same data, while in the process case, I require something much heavier, okay? What is the state of the operating systems with relation to threads and processes? So you have a little bit of this, a little bit of that. Some OS only supports processes, and threads are some kind of special processes, like lightweight processes. Some OS supports only threads, and call processes threads groups, okay? Threads groups. While some OS natively supports both concepts, okay? We will come back to this later when we study synchronization, okay? So process, conclude, abstraction of memory space, resources, thread, execution flow, okay? The scheduler manages threads, okay? Processes do not normally share memory. You can allow them, but it's a heavier process, it's a heavier task. Two threads share the same memory. Threads may communicate in a shared memory paradigm or in a message passing paradigm. In the following slides, when we will study synchronization and communication, semaphores and so on, we will refer to threads, to different threads, concurrent threads, sharing the same address space, okay? So the next set of slides, okay, refers always to threads sharing resources, okay? Questions on this part? Otherwise I will put it on Dolly at the end of the class, and I will start the concurrency, synchronization, and so on. So this part, pay attention, because this one will be the subject of the written exam. Okay, so written exam will heavily depend on this part, as well as on the synchronization communication exercises that we will make throughout the course. Okay? So potentially you will be able to pass the written exam already within 3-4 weeks, let's say, okay? Okay, repeating myself, need for concurrency is better from a functional perspective, because you can better separate instances, different execution flows, different instances that need to function at different periods. One need to be more frequent, one less frequent, and so on. Okay? If you have different separated execution flows, you have a further degree of liberty to better express your functional, okay, requirements, the functional behavior of your application, also in a much more efficient way, we said. When we need these instances to communicate between each other, it's a much lighter process when we use threads, okay? And we have, of course, by construction, we have a better expressive power, okay? We better can express the functional dependencies and the different execution flows. So, in terms of performance, in a single core setting, the performance comes from making a better use of the waiting time. Okay? In the example we saw before, whenever I need to wait for something before continuing, if I'm in a concurrent environment, I can express that with two different threads, one that blocks and the other one that executes instead. So instead of wasting processing cycles in waiting something, I can execute something else. Okay? This is really the main contribution of having concurrency in single core settings. Okay? The word processor example that I made before is just a stupid example, but take for granted that a lot of activities, almost all activities that you execute on your computer have something of this kind. You're always waiting for something. You're always waiting for someone to press, someone to move the thing, some other process to complete, the printer to finish, the data packet to come from internet. It's always waiting for something in our computers, okay? So that's why we don't have just one single execution flow, but we have multiple ones. Of course, in a multi-core, that comes even easier because you have further cores where to execute. So you can only increase performance if you have a concurrent expression of your program. So the expressive power, many control applications are inherently concurrent. I said before, in control, you typically have different periods. You typically have different activities that need to be updated with different periods. It is a waste of time using one single period, one single thread to perform all of them. Okay? Okay, so in the theoretical model that we use, we will always assume a set of concurrent activities. They may be either processes or threads, and they interact in different ways. They may access the hardware resources. It may be the processor, the disk, I/O, memory, or they may exchange data between themselves. Okay? So the activities typically compete for the resources or they cooperate for some common objective. A resource, according to what we said, may be a hardware resource, for instance, the Ethernet controller or the CAN bus or whatsoever, or it can be a software resource, maybe a data structure, a table that you have in memory, okay, a list, a queue, whatsoever. This is a shared data structure. For instance, you have two processes that would like to write to the same queue, okay? The queue is the shared data structure, okay? Hardware, when you have like a CAN bus and two processors need to communicate to the CAN bus. The CAN is the backbone in the automotive domain, the communication backbone. Okay, so in both cases, accessing the resource has to be regulated. You cannot just allow the process to read and write whenever they want to a shared resource. Imagine in an Ethernet controller, you cannot dirty the packet of one sending message with the content of the second message, okay? In a shared data structure, if I'm updating one line of a table, I cannot allow another task to rewrite, overwrite part of that line, otherwise the content will not be consistent, okay? So I need to regulate atomically the execution, the access to these shared resources. Again, either hardware resources or software resources. Okay? These should be regulated. If two processes want to print on the same printer, of course, if both processes send the message together, you will not print something meaningful. Okay? That makes sense. If you two access share the same data structure, you risk inconsistencies if you don't synchronize the access to it. So we will analyze both shared memory and message passing in the following slides, okay? Both shared memory and message passing, okay? Again, competitive concurrency you have when different activities compete for resources and one process is not aware that another process exists. So for its functional behavior, it does not rely on the other concurrently executing processes. In a thread-based model, multi-threaded environment, in a cooperative concurrent setting instead, the functional behavior of that thread strongly depends on the functional behavior of the other ones, okay? They cooperate, okay? In the competitive concurrency, it is the OS responsibility to manage the resources to avoid conflicts and to be fair. While in a cooperative, multi-threaded environment, it's the responsibility of the threads to properly synchronize themselves in order to achieve a desired behavior, a desired goals. Okay? Every activity knows about the other ones, and they must synchronize on particular events. Okay? I'm repeating in different ways, more or less the same concept, just to fix it in your brains. So there are different synchronization paradigms if you use a cooperative or a competitive model. Competing activities have to be protected one from another. Okay? They do not collaborate, they compete. So we typically assign different address spaces. If one of these activities tries to access a memory region which is not in his address space, you typically have a segmentation fault, something of that kind, okay? You have an exception, okay? Separate memory spaces. The allocation of the resource and the synchronization has to be centralized, okay? So you typically have a central manager, typically the OS, or some resource-dedicated process, which allocates the resource in a hopefully fair way, or according to some policy, okay? The communication is typically a client-server model, okay? If you remember before, we assigned a process as a manager of a resource, okay? So the process that requests this resource is the client. It sends a request to the other resource manager process, which is the server, and it responds back, it answers back to the first one. Okay? It's a typical client-server model. Okay? It's more suitable for a process model of execution. This is the typical implementation. So the server, it manages, it has exclusive ownership of the shared resource. It may be a queue, for instance, okay? A shared data structure. If a process would like to access that, so if two clients would like to access the same server, it is responsibility of this server to arbitrate who to give the access to the shared resources to, okay? Client server. This is the typically implemented with message passing primitives, and these primitives often are called send and receive. Okay, you may have already heard about that. Okay, so this is the message passing paradigm. The server sends back the responses when you write a send. It may be a blocking send, a synchronous or an asynchronous send, and the same when the client waits for the answers back of the server. So it may be a receive, which is a blocking or non-blocking, synchronous or asynchronous receive. Okay? The server doesn't need to be on the same chip, on the same core, or on the same processor. Okay? It can even be on a remote system. Okay? This is typically implemented in message passing system with MPI or distributed computing systems. While again with cooperation, we know that each thread knows about the others. We do not need to ensure memory protection. Okay, we have less overhead. They access natively the same set of data structures. The allocation of resources is decentralized. The allocation of resource is decentralized. It means that now you don't have a resource manager. You don't have a process which is exclusively dedicated to that resource and receives the sends and sends back the answer. Okay? You don't have that. You have multiple threads that know about each other, and this is what you will do in the written exam. So these threads need to properly synchronize so that you guarantee data consistency. Okay? And you typically have that in the shared memory model, so in the same architecture. So competition typically comes with message passing. It's not mandatory to solve competition through message passing. You can also use a shared memory. It's just more easy to implement competition with message passing, send and receive. Okay? While cooperation is best suited to shared memory paradigm. Okay? Again, I can implement cooperative concurrency even in a message passing. Okay? But it's more natively implemented, okay, more easily implemented. It easily matches the shared memory paradigm. Okay? Multi-process, multi-thread. Okay? Again, I can implement both in the other way around. I can. Just it's more easy to match them in this way. Okay? In general, the operating system supports both primitives, both execution models, both communication models. They support protection for competing activities, so the notion of process. They support the message passing primitive, send and receive client server, okay? And they support shared memory for reducing overhead, okay? Still, there may be some microkernel which implement just one of those. So some real-time operating system only support shared memory, some of them, okay? Only support shared memory without implementing separate memory spaces, okay? So you need separate memory spaces to implement the multi-process setting, okay? Okay, now let's dive in the shared memory model of concurrency. is the first one that has been supported, right? Because you had one memory, multiple processor, multiple threads, and you just needed to implement that at OS level. Is the closest to the machine, because again, in the machine you have one memory, one physical, okay, memory, and you have multiple threads, okay? All threads may access the same memory location, and it's up to you, programmer, to synchronize them to maintain consistency. An abstract model presents a good analogy is when the many-core, the multi-core model. So instead of having multiple threads, I here have multiple CPU. Okay? Instead of having one and only memory address space, I have one and only physical memory. Okay? Not the same thing, but it's more or less the same metaphor, the same analogy to what we said before. So how can I grant the resource to one thread or another? I can have different resource allocation models. So static or dynamic. A static allocation of resource means that once the resource is granted, it is never revoked. So if a thread has a lock on a resource, I will never preempt that lock, thread on that resource. While in the dynamic way, the resource can be granted and revoked dynamically. So there is a manager that decides, okay, when and if a thread should be kicked out of the ownership of the lock on that resource. Then, the access to a resource can be dedicated or shared. So dedicated means that only one activity at a time may access that resource, while shared means that many activities may access that resource at the same time, okay? In which case, you need to guarantee mutual exclusion. So while one is operating on that resource, the other one does not interfere with that, okay? So, what is the problem here when you need to synchronize activities, multiple activities sharing a single resource? The problem is that we don't know when these activities, these threads, will request access to that resource. I don't know how they will intertwine between each other. I don't know which one will come first and which one will come second, okay, which one will read, which one will write, and when. So we don't know in advance the order of execution of the instructions. Also, when I increment, so when I write code, you perfectly know that that code, so an instruction, C++ instruction, which is x++, is expanded into multiple instructions. Load x, increment that register, and store that register to memory. Okay? This is at least 3 instructions. Okay? So we don't know how much will it take for each instruction to execute. So we cannot take for granted the timing at which a resource will be accessed. So we will need to perform operations on shared resources in a mutual exclusive way. We will need to implement atomicity. So we will need to perform operations, critical section, that will not be interrupted by other operation accessing that very same resource. Okay, this is the notion of atomicity. So for an instruction, the atomicity is also a concept that you find at the architectural level. So there are instructions, hardware instructions that, of course, are atomic. You cannot interrupt a hardware instruction at hardware level. Okay? So they are not interfering with other instructions. Okay? Atomic operations are always sequentialized. Also, atomic operations cannot be interrupted. So they are safe operations. So transferring one word from memory to register is one operation. Do it the other way around, it's another operation. No atomic operation may be interrupted, okay? While the operations that are non-atomic are more risky, so they can be interrupted during their execution. So they are not safe operations. They may end up to inconsistent scenarios. So non-elementary operations, typically X++, are non-atomic. Okay? Let's see it. Okay? Probably examples are the best way to understand what I'm saying here. So X++ in assembly is expanded to load X from memory and put it to one of the registers. Increment that register and then store back X, okay, that register to the X memory location. Okay? Okay, this is non-atomic. Okay? Each instruction is atomic, but the three of them is non-atomic. Okay? So this instruction is non-atomic. This instruction is non-atomic. Okay? It is expanded into these three ones. Okay? If I had another process that runs the same operation, okay, it may be interfering, depending on the scheduler, with this execution flow. We will see this in the next slide. So this is the example. So you have a one thread, thread A, which does that operation, and thread B, which does the same operation. Okay? If there are two calls, one to thread A and one to thread B, and your X value was initially 0, at the end you would expect 2, right? Plus 1, right? 1 plus 1 is 2. Of course, this is not the case when you have non-atomic operation. So 1 plus 1 does not make 2. Okay, 1 plus 1 leads to 1. Look at that if you don't believe me. I load the value of X to the register for thread A. Okay, load X to the register. X was 0, so I have in R0, I have 0, okay, thread A. Then I have a preemption, non-atomic operation, okay. The scheduler may decide that now thread B arrives, I have an interrupt, then a scheduling decision, thread B is higher priority, so I start running B, okay. What does B do? So what is this step here? This is a context switch. This is a context switch. Okay? You remember what happens in a context switch? This is a thread switch. Okay? What was the only memory region which is not shared among different threads? You remember that?
No.
What was the only memory region in the multi-thread model which was not shared? The stack, exactly. So the stack is exclusive, it's proprietary of the thread, okay? So before switching thread, this guy saves his registers to memory, saves the stack pointer to memory, okay? When it will rerun again, it will pop the stack pointer and it will refind whatever it saved before, okay? The stack, okay, is not shared. Stack is proprietary of the thread. Okay, so thread switch. Then B starts operating again. So it reads X, stores it into the register 0, increment the register 0. Okay, X is still 0. This is the shared memory variable. Okay, this is my shared memory variable. Increment R0, so X is still 0, but the register is 1, and then I store R0 to X. So X eventually become 1. For now, so long, so good, okay? Then, this finishes execution. We have a context switch, okay? We have a thread switch, okay? We restore again the stack of thread 1, okay, of thread A, which will refine again is R0. R0 was 0 here. It increments R0 to 1, and then it stores back 1 to X. So it rewrites 1, but X was already 1, okay? So you can see that at the end, x is 1 instead of 2. Is this what we wanted? Of course not. Okay? This is the simplest possible example of why you need atomicity, okay, when implemented concurrent programming. Okay? This should be crystal clear in your brain, because we will see much more complex examples than this one. Okay? The problem of implementing concurrency is also an application you find in industry, is that people is not able to deal with that. People is not able to understand when threads can operate on the same variable. They don't know how to guarantee atomic execution, to the extent that to guarantee that those threads do not interfere, they just lock one global lock at the beginning of the thread and one at the end of the thread. And then they go to me and say, but we lose in performance. Oh, surprisingly. Okay? So we need to understand how to perform locking, mutual exclusion in an efficient way. Okay? Second example. So, second example here. Let's take a look at this code here. We have now the shared structure. It's not just one single variable, it's not just x. But we have a structure of two integers, a and b. Okay? Just to make a slightly more complex behavior. So then you have multiple functions, okay? You have thread A, which would like to increment both variables. And you have thread B, which would like to multiply both variables of that shared structure. Okay? Again, data structure A shared by both threads. What are the primitives, the interface, the functions associated to this shared data structure? I may have an initialization primitive that sets to 1 A and B. Okay, I performed it. Now A and B are 1. I may have a double increment. I increment A by 1 and I increase B by 1. And I can have a multiply by 2. I can multiply B by 2 and A by 2. Okay? Okay? Note here I first multiply B and then I second multiply A. So I have a consistency property here, consistency property, because these are the only functions that I can operate the data structure with. And all of these functions operate on both variables. So A and B should always have the same value. Okay, A and B should always have the same value. This is a consistency property that I would like to maintain in this case. Now, if I assume that A would like to increase both variables and B would like to multiply both variables, but threads may be intertwined in a nasty way, you don't guarantee atomic execution, you don't guarantee the atomicity of these and the atomicity of these, then what can happen? Look at here. So thread A starts and increase A by 1, so A becomes 1 plus 1, 2. Then it turns on thread B, which starts executing his first instruction, multiplies B by 2, so B becomes 2. Then maybe thread A again, which increases B, so B was 2 and now it's 3. Okay? And then it's thread A again, sorry, thread B again, which multiplies B by 2. At the end, you have 3 and 4, which is, of course, a non-consistent state. Okay? Different example, same result, same inconsistent result. So this was not due to the assembly expansion, this was due to the fact that these functions are not executed atomically. Okay? It is perfectly possible that the scheduler may decide to execute first one instruction, then one of the other thread, and so on. So what is consistency? So consistency depends on your program, on what you would like to enforce. Okay? If you have a student table with the register number, the birth date, and so on, you would like that you don't have a name of one student and the birth date of a second one in the same line, right? This is a kind of consistency. You would like, in the slide before, to have two variables having the same value. So consistency in general is a Boolean expression on the values of the internal variables. So consistency means, take the case of I want the previous data structure to have both variables with the same value. Okay? So consistency should apply before and after an operation. So an operation maintains consistency if the consistency property is verified before and after its operation. So take the example of the increment, of the double increment, okay? Increment A and increment B. When I call the increment, while the increment function executes, I first increment A, so A is higher than B, so consistency is not called, is not held, but then I increment B. Okay, so at the end of my increment instruction, consistency is restored. So it is a consistent operation because the consistency property holds before and after the operation. So it does not hold when I perform the increment, of course, because in order to implement that operation, I should first increment one of the value and then the other one. Okay? But consistency should hold before and after. Okay? So we have a formal way to verify that. So let R be a resource and let CR be a set of consistency property of the resource. Then we have that CR equals to the set of consistency properties. So a concurrent program is correct. Concurrent program is correct if we guarantee consistency for every possible interleaving of operations. So we know for sure that every possible way the task may arrive, be executed, scheduled, and so on, the consistency property is guaranteed before and after each operation. Okay? Concurrency does not talk only about functional correctness, but the functional correctness depends on this consistency property, which should guarantee along the lines of the execution of my concurrent program. Okay, let's start to see a little bit more complex example. So a circular array. Okay, let's become familiar with this circular array structure. Okay. Did you see already circular array? It's nothing special, right? It's just an array that is circular. So the end of the array matches back to the head of the array. So the tail goes to the head, so you can circulate. Okay? So you have an array, for instance, with 10 slots, and you had the index of the head, of the current head, the index of the current tail, and the number of the valid elements that have been inserted. Okay? So how is this initialization part? At the beginning, the circular array is empty. It is empty, so the number is 0. Okay? It's empty, so the number is 0. You have the head, which is 0, and the tail, which is 0. So head and tail points to the beginning of your array. Okay? And the number of valid elements inserted is 0. Okay? So then I have operation. I have the two basic operations, which are insert something in this array and extract something from this array. So insert something. So first a check. So if the number of elements, of valid elements, is 10, what does it mean?
It's full.
It's full, right? So the array is full, so return, okay, I wasn't able to insert anything, okay? Otherwise, I can continue. So, A head, A array, element. So, insert the new element, okay, to the position denoted by the current head of the array. Okay, I insert the new element in the first empty slot in what is the head of my array. Okay? And then I need to increment the head, right? Because for the next insertion, I don't want it to overlap with the one I just inserted, so I will just increase the head by 1, but it is a circular array, okay? When I reach 11, I would like to fall back to 1, okay? So it's a modulo 10, okay? Modulo 10, okay? So if it is 10, 10 plus 1, 11, it goes to 1, okay? And then, of course, I inserted a valid element I increment the number of valid elements, plus 1, okay? And I return success, right? Extraction. What shall I begin checking for an extraction? I need to check this. What is this checking? The array is not empty, right? If it is empty, I return failure, okay? Then I extract to the address, to the pointer that I give him as a parameter, as a functional parameter to return. I return it, I copy the tail. So I insert from the head, I insert to the head, and I extract from the tail, okay? While the array grows in one side and decreases on the other side, okay? And so on. It's a circular thing, okay? So I copy the tail and I decrease the tail. So I increase by 1, okay, the tail, and I decrease the number of valid elements. Nothing special, right? If the tail is 11, then it goes back to 1, and the number of elements is decreased by 1, and then I return success. Okay? Nothing special, okay? Circular array, programming 1 courses. Okay, what are the consistency properties in this case here? There are multiple consistency properties that I would like to assure. Okay? We can go through them together. Okay? Assume for now that the increment of the number here and the decrement here are atomic. So assume they be atomic for the moment. So first consistency property is that when the array is full or when it is empty, then the head coincides with the tail. Okay? Head and tail are at the same position when the array is full or when the array is empty. Okay? This is one of the consistency properties. Another consistency property that I have is that the number of valid elements that have been inserted whenever, okay, I insert something is given by the index of the head minus the index of the tail modulo 10. Okay? This holds whenever the array is not full or empty. Okay? So if I have 2 elements, typically 2 is the result of the index of the head and the index of the tail. So if the head is 7 and the tail is 5, then the number of elements is 2. If the head instead of being 7 is 3, then I need to count, okay, the modulo 10 factor, okay, and I end up computing the number of valid elements. Another consistency property is the number of valid elements matches the global number of inserted elements minus the global number of extracted elements. So I don't want to lose elements around. Okay? I don't want to lose elements around. Then there is a consistency property for the insertion operation. So if the number of elements is less than 10, then I will have that the number of elements increased by 1 at the end of the operation, and the last inserted element is to the position minus 1 of the head. Same for the extraction operation. If the array is not empty, then the number of elements decreases by 1, and the tail is tail minus 1. Okay? The extracted element, is the 1, tail minus 1. So, circular array shown in graphics, okay, with a scheme just to hold it better in your mind. So the initial state, empty, okay, head, tail coincides, number of elements 0. I call insert. I would like to insert 5, okay, I insert 5. Now the head is 1, the tail is 0, and the number of elements is 1, right? Continue. The consistency property hold C2, C3, and C4, which are the one called here when I do a perform insertion. Okay? Just to remind you what were this consistency property, you can see that they all hold. So the number of insertion minus the number of extraction is 1, and the number is 1, and so on. Okay, I'm not re-repeating. You can check it offline. Then I continue. I do an insert of a 3. Everything works best. Now the head moves further up. Okay? The tail continues being there. Okay, this is the situation. Again, the consistency property hold. Okay, continuing. Assume this is the current situation of my array. Okay, the head is at 9. So at the end of my array, the tail is at 5, where the 1 is, and we have just 4 elements inserted. Okay, I would like to insert the 10th one. Okay, here. Okay, now the head increases by 1, and it goes back at the beginning. Okay, this is the situation. Again, the consistency properties, you may check it home, you may check them home, they all hold. Okay, this is the final situation. Let's check them for the extraction operation. Okay, this is the extraction. I extract one element, which is 1. Okay, I increase the tail goes there. Okay, this is the situation, and again, now it's C2, C3, and C5, the extraction related consistency property, all hold. Okay, now that was the easy part. Now assume that we have two concurrent processes trying to make the same operation. Try to perform the insertion operation. You may guess that this may lead to consistencies problem like we saw before if we do not guarantee atomicity. Okay? So what can happen? So this is the initial state. We call the first thread TA, thread A, to insert 5. Okay? And we call thread B to insert 2. At the end, we would like to have 2 and 5 inserted in the queue. Okay? This is the code for thread A, this is the code for thread B. Unfortunately, they may interleave in a bad manner, okay? In a nasty manner. So we may end up having, let's see that together. So thread A performs the first operation, the array is not full, so I can continue. Then I insert the 5 in the head. Okay, so it will write 5 there. Okay, before updating the head to the next position, so before moving the head to the new position, it is preempted by thread B. Okay, which thread B will insert a 2, so it will overwrite the 5 of the first thread, and only then increase the head. Okay, and increase the number. When A will execute again, it will increase further up the head and increase the number. So at the end, what we will have? So this is the 5, this is the 2 which is overwritten, okay? The 2 which is overwritten by B. The head, due to the B operation, is increased by 1, and due to the A operation will be further increased, okay? Like this. Now we have the head here, but an invalid position, an invalid entry here. Consistency property is violated. Okay? 5, the last insert element, is different from head minus 1, and also the number of valid elements is different to the number inserted. So this program is not correct. Okay? Looking at the code, you may think it is correct, but it is not. When executed in a multi-threaded environment in a non-atomic way, this is a wrong program. So it exists. Why is it not correct? Because it exists a possible interleaving of insertion operation such that the resource is left in an inconsistent state. Okay? It was not difficult to prove that the program is wrong. It was not a problem to prove that there is a consistency miss. Okay? There is a consistency problem in the program. How did we prove it? With a counterexample, right? We provided a counterexample and we proved that the program has at least one instance, one possible interleaving, one possible arrival, time, and scheduling that leads to a nasty effect, to a consistency miss. Okay? However, if we wanted to prove that a program is consistent, if we wanted to prove that a program is correct, a concurrent program is correct, this is much more difficult. So you prove incorrectness with one counterexample. To prove correctness is much more difficult, okay? You need to analytically think on whatever may happen, okay? So, what if an interest and an extract are interleaved now? We can think, so we saw before two insert together, right? We saw before two insert together, and we discovered that this may lead to an inconsistent behavior. What if we now would like to have one thread performing an insertion and just a concurrent one performing an extraction, okay? So we would like to see whether this leads again to an inconsistent state. Well, the answer is no, it doesn't lead to an inconsistent state. It still maintains consistency. Again, if I have two threads, one that inserts and the other one that extracts, this will not cause consistency problems, okay? If you have just one and just one. How can we prove consistency? So, we can prove it that way. So, if the array is not full or empty, well, the insertion acts on one side, the extraction acts on a different side. Head and tail are different, okay? So this is the last thing that we see today. I will leave it for Comb to think better about that. So insertion acts on the head. So it writes the head and increases it. Extraction, it pops the tail and increases it, okay? And increases it, okay? And both updates the number, which we assumed is atomic. We assume that the num++ is atomic. It is not, but for now we assume that num is atomic, okay? So insertion and extraction act on separated shared memory instances, okay? One acts on head, the other one acts on tail, as long as the array is not empty or full. Okay, so they do not interfere each other. They cannot cause an inconsistency problem. Okay, what if the array is empty? Okay, it happens that extract CA, if extract CA, now you need to think about the possible interleavings. So you may need to think, what if extracts come first and insert come next? What if insert come first and extract come next? Okay? I told you it's much more difficult to prove consistency than to prove inconsistency. Okay? So think. So if extract begins before, okay, what happens? Extracts, when the number of elements is 0, immediately returns 0. So again, no conflict. Okay? Again, nothing bad can happen. What if instead insert starts before? Okay? Extract still will return false. So, no problem, no interference with the insertion process. You have a dual effect when the array is full. So, insertion will always fail. Okay? It will fail. So, before, sorry, this is, if insert begins before, extract CA will return false. No, this is wrong. So, yeah, this is wrong, so I have to change it. Avete capito, no? Cosa è sbagliato qua?
Deve tornare vero, cioè
esatto, bravissimi. So, nel caso, in the case where insert CA begins first, okay, you will have extra CA will fall back to this example here. So, extract will have one valid extract CA will return true. Okay, so well, this requires you to go along the code of both things, and you will see that since num++ is atomic, this cannot cause to any problem. Okay, this cannot lead to any problem. For the case when the array is full, you have the other way around. Okay, now it's the insert that fails if it comes before, while if it is extract that comes before, then insert will just find everything that works. Okay? We will continue from here next Monday, okay? Start a little bit thinking about the examples that we saw today, okay? This is the better training, mental training for you guys to learn concurrency, okay? See you on Monday. Have a nice weekend.
Little request. As I take notes on my tablet,
Okay.
it would be very useful if you upload the slide.
Before the class, right?
Yeah, even 1 minute before, but
Okay,
it would be
I will try
better.
to do that,
Yeah,
yeah.
I can write on it and I can.
Okay, I will try to do that.